Hi, so this video will be about how do we actually quantize a tensor? What does it mean to quantize a tensor? What are the different kinds of quantization? What are the basic recipes? What's happening in hardware? So this video will be a general overview of what is happening in quantization when we quantize a floating point tensor. Okay, so how do we quantize a floating point tensor? So I'll just be giving a quick presentation on this. Topics like how does neural networks actually work on hardware? What are the differences with int8? What is fake quantization versus conversion as related to int8 models? How do we actually do fake quantization of tensors? What is symmetric versus affine quantization? How do we actually determine these quantization parameters that we're going to need? And quantization granularity, i.e. per-tensor versus per-channel quantization. So let's get into it. We have to understand how neural networks work in hardware to begin with. So the way matrix vector multiplication is implemented in hardware is via these multiply and accumulate MAC operations. We load in our weight tensor, we have our inputs, it does these multiplication operations, and then they get accumulated. It's fairly simple, fairly easy, and this is highly parallelizable, and this is one of the reasons neural networks have become so popular in recent decades, is because we've gotten hardware support for neural network operations, which have made them, feasible in terms of training and to run on hardware. If the previous slide was for any arbitrary numerical representation, let's say floating point, the way it works in int8 is slightly different. So we see that our weight tensor gets quantized to int8 and the inputs get quantized to int8 as well. And then all of this multiplication, it takes place in int8 space. So it can take advantage of all of our integer arithmetic. It comes with all of the associated speedups and power reduction. But when you do these multiplications and then when you accumulate them, that accumulation happens in int32. Depending on your hardware, sometimes it will happen in floating point 32, it varies. And the reason for this is fairly simple. It's just because if you take an arbitrary number of int8 numbers and you multiply them together and you add the results, that value is not going to fit into 8 bits most likely. So to prevent overflow errors, you need to have this in a higher bit range, int32 or floating point 32. However, if the input is in int8, ideally the output would also be in int8 so that when you feed it to the next layer, that is also going to be int8. So we have this requantization step, which takes the output feature of this layer, also referred to as the activation. And this is very common in int8 nomenclature, that you will hear reference to the weights and you will hear reference to the activations. And the activation is the output feature of the layer. So just for your knowledge. So yeah, this activation, we have to requantize this, and that just means you round it down just depending on what your quantization parameters are going to be, and that gives you another int8 tensor, and then it keeps on going, and this may get fed into another layer. So that is how that works in int8. Okay, so the question is, we have our PyTorch models or TensorFlow models, but my understanding is that most people work with PyTorch these days. PyTorch trains typically in floating point 32, but we want int8. So how do we bridge that gap? The way it is done is via something called fake quantization. Basically, your model is still floating point 32, but the tensors are snapped onto this int8 grid. So they're rounded onto this int8 grid. So again, all of your tensors, they're still floating point 32. They take advantage of all of the different PyTorch techniques that are optimized for floating point 32, but your tensors are snapped onto this int8 grid. That's what we refer to as a fake quantized model. That isn't a true int8 model. It isn't doing all of the integer arithmetic and taking advantage of all of the benefits of int8, but it should be numerically identical. It should be. And then a true int8 model is referred to as a converted model. So typically when you're working in PyTorch, you'll do everything in quote unquote fake quantized space. You'll do all your optimization in that space. But then when it comes time to actually creating a true int8 model, you'll do a model conversion. It's very easy. I'll have videos on this. and that will give you your converted model, in other words, the true int8 model. In theory, the fake-quantized model and the converted model should perfectly match. There can be reasons why they don't, and debugging the reasons for that is going to be an entire different video. There's lots of things that can happen there, and yeah, I'll make an entire video dedicated to just model conversion. Okay, so how do we do this fake quantization of tensors? There are two main quantization parameters you have to care about. They will define how we derive this fake quantized tensor. In this equation, there is a third quantization parameter, this b value, but that just stands for the bit width. So in int8, that's going to be equal to 8. In int16, that would be equal to 16. In int2, that would be equal to 2. Basically, we're going to ignore this forever as long as we're in int8 land. The other two quantization parameters that we care about are the scale and the 0 point. The scale is responsible for the scale of your quantization range, and your 0 point is responsible for the offset. I'm going to show this with an example. We're going to take a floating point tensor, and this tensor is going to have a minimum value of 0, and then the maximum value of the tensor is going to be 1. So it's going to have a dynamic range of 1, going from 0 to 1. And these are what would be reasonable quantization parameters for this tensor. Now, how to derive quantization parameters, I'll talk more about later. But just as an example, we're going to go through this equation and see what happens to this tensor when it gets fake quantized. Let's take the minimum value of 0. 0 is going to get divided by the scale, which we said is 1,255. That is just going to be equal to 0 with this rounding operation. We're going to add the 0 point in, and that's just going to be, again, 0. So the minimum value of 0 in floating point gets mapped to 0 in this integer space. Then it does this clamping operation with a minimum value of 0, and then the maximum value of what in this case is 255. You can maybe get an intuition as to what's happening here. We've rounded down this floating point to this range of 0 to 255. And then the 0 point has represented this offshift. We clamp, we make sure there's nothing outside of this quantization range. So now the tensor is on a 0 to 255 scale. Because of this rounding, we ensure that everything is on this grid. Everything is equal to either 0 or 1 or 2 or 3 or 4, all the way up to 255. Then we send it back up to the original scale. So we add this 0 point in, technically we're subtracting it back in, and then we times by the scale. And what that's going to mean is that in this fake quantized tensor, it's going to be on the scale that it was originally, 0 to 1. But all of the values in that tensor will be limited by whatever our quantization range was, which in this case is 0 to 1. And all of the values are going to belong to this int8 grid. So values are going to be equal to s times 1 or s times 2 or s times 3, all the way up to 1, which is 255 over 255 times s, which is equal to 1. Okay, hopefully that made some sense. Let's look at a second example. In the second example, we're going to take a tensor, and the minimum value is going to be -1, and then the maximum value is going to be 1. The scale is again given by the dynamic range of this tensor. So in this case, the dynamic range is 2. Hopefully we're building some intuition as to what the scale parameter represents. It represents the ideal quantization dynamic range that we will have. And then the 0 point is going to be 127. Why is this? Well, the 0 point, it should be interpreted as a value between 0 and 255. In theory, you can have negative 0 points. You can have 0 points that are larger than 255 for int8. But practically speaking, and this comes into a bit of nuance, when you're actually trying to deploy your model to hardware, let's say Intel or Qualcomm, sometimes those SDKs will enforce that your 0 point is between 0 and 255. So if you have a negative 0 point, for example, which can happen, that won't work. For example, I know I'll link the documentation for Qualcomm, for example, but in Qualcomm, it enforces a 0 point between 0 and 255 because the 0 value needs to be representable in that quantization range. So it's something to be aware of. Typically speaking, your 0 point will be between 0 and 255 anyway. If not, you might have problems when you take your model and try to put it on hardware. But why is this value 127.5? Well, what that should be interpreted as is that there's half of the quantization range is negative and half of it is positive. And so we can go through this example. We take this minimum value of -1 divided by the scale. That is going to give us, what is that going to give us? That's going to give us, I think, -255 divided by 2, which is -127.5. That's going to get rounded, and we'll say that's -127. And then we add this 0 point, which is 127.5. In practice, when we actually do this fake quantization operation in PyTorch, this 0 point, it might be equal to 127.5, but it gets rounded, yeah? And not that you will probably ever need to know this level of detail, but the way it gets rounded is that it gets rounded to the nearest value unless it is halfway between two values, but in this case it's 127.5, and then it gets rounded to the nearest even value. You will probably never need to know this, but this is the level of detail that you sometimes have to go down in int8 when you're debugging stuff. So for your awareness, this 0 point will get rounded to the nearest integer or the nearest even value in case of a split. So we said that when we round this, we have -127. We then add this 0 point in. Oh, what do you know? This is 128. Well, okay, we'll say that this got rounded to -128 for the sake of symmetry. And then when we add 128 to it, that brings us again to 0. And so again, we see here, it's a better example of what the 0 point is actually doing. It shifts us into this 0 to 255 range where we do our clamping. And then the same thing happens, is that we add the 0 point back in, we get shifted back to the -128 to 127 scale, and then we get multiplied by the scale value again, which is going to bring us to this -1 to 1 dynamic range. Again, the quantized tensor is going to belong now to this quantization grid, so values will be equal to -1 to -1 plus 2 divided by 255 all the way up to 1. So there'll be 256 discrete values in this tensor. Cool. What about the different kinds of quantization? Well, what I just presented is called affine quantization, and I presented the more difficult one first because if you grasp affine quantization, symmetric quantization is going to be very easy. The difference between the two is that affine quantization has a 0 point, so it has this ability to be offset, versus symmetric quantization has no 0 point. So symmetric quantization, by definition, it has an equal amount of negative quantization range to positive quantization range. This can be good and it can be bad, because for symmetric quantization, it can be a bit frustrating if you're doing symmetric quantization and you are trying to quantize, let's say, the activation of a conv ReLU layer. The output of a conv ReLU layer is strictly positive. It can be equal to 0 or some positive value, but it can't be equal to a negative value. And if you're using symmetric quantization for that, half of your entire quantization range is going to be unused, which means that effectively you don't have 8 bits of quantization space to play with, you have 7. So that can be a downside of symmetric quantization, but the upside of symmetric quantization is that it's significantly faster, particularly for weights, and because it is significantly faster, there are some hardware platforms that only support symmetric quantization. Affine quantization is fairly broadly supported, but NVIDIA's TensorRT framework, for example, if you want to run your int8 model on TensorRT and NVIDIA, they only support symmetric quantization. They do not support affine. If you read the white paper on neural network quantization by NVIDIA, they give a very detailed mathematical explanation as to why symmetric quantization is more hardware efficient than affine quantization. The benefit of symmetric quantization tends to be, especially for weights, if you are quantizing the weights, it really heavily benefits from symmetric quantization. And that's typically okay because weights tend to be symmetrically distributed anyway. It's mostly specific kinds of activations that are, let's say, strictly positive, in which case affine quantization works for those. But again, it's this trade-off. Depending on what hardware you're trying to target, you might be limited to symmetric quantization. And also there is something to be said about if you're using a conv ReLU and you want to use affine quantization, but you find yourself limited to symmetric quantization, That could be a good opportunity to explore something like a leaky ReLU or a pre-LU, because that way you also benefit from the negative quantization range, and that's not all zeroed out. So that's just food for thought. But yeah, this is symmetric versus affine quantization. Okay, so the next question is, how do we determine these quantization parameters? How do we determine this scale, or this scale and 0 point if you're doing affine quantization? One way is to just manually set them. Let's say, for example, you have an image tensor, and normally that's literally already perfectly quantized, right? Because RGB values tend to be on a 0 to 255 scale anyway. If you divide that by 255, all of your values of your tensor will be on a 0 to 1 scale, and they will have, a spacing between every single unique value of 1 over 255. In which case, you know exactly what the quantized range of your tensor should be anyway, so you should just manually set them in those cases. And there are quantization configurations that you can use to do that, called fixed Q-param, Fake-quantize. We'll go all into this in future videos. Another possibility is, if you can't manually set them and it's not correct to manually set them, you don't know what the quantization parameters should be, for example, if it's some activation or a weight in a deep layer, the second way to determine quantization parameters is via observation. So typically we do what's called post-training quantization, also known as PTQ, and this involves, for weights it's easy, you just observe what the distribution of the weight is, and based on what is called PTQ observer, you can observe roughly what the quantization parameters should be. Let's say if you're trying to minimize clamping error, or you're trying to minimize the mean squared error between your quantized tensor and your floating point tensor, or the KL divergence. There's a lot of different metrics that we can use to try and estimate the quantization parameters. It will typically depend on your model, but observation is one way to do it. For weights, as I said, it's easy. You just have to look at the weight tensor. For activations, it's a bit more difficult because you have to feed calibration data through your model, and you have to have a hook to observe what the activations look like. And then it's the same thing. Like, either you're trying to minimize clamping error or mean squared error between the floating point and the quantized tensor, or the KL divergence, or you're trying to minimize the clamping to some percentile. There's a bunch of different what we call PTQ observers, and what you trying to minimize as your loss function will depend on what observer you use. The third way to learn to derive quantization parameters is via learning. So, for example, you can literally just train your model. You can make your quantization parameters learnable parameters inside of your model, and then you can do what's called quantization-aware training. Typically, the workflow will involve doing post-training quantization to get an initial estimation of what your quantization parameters should be, and then you do quantization-aware training, where you quote-unquote fine-tune those quantization parameters. And this will typically involve, when you're feeding the data through your network and all of your activations and weights, they will be in Fake-quantize space. They'll have these learnable quantization parameters, and they will be trained via gradient descent, depending on what your loss function is. It could just be your normal loss function, or you could add in an extra loss function that's specific to the quantized parameters. But that's an entire different story, and we will go into post-training quantization, we'll go into manually setting quantization parameters, we'll go into quantization-aware training, all in future videos. But this is just for your general awareness. This is how we determine quantization parameters. Okay, last thing is quantization granularity, because in theory you could quantize a tensor either on a per channel basis or on a per tensor basis. Now, it turns out that for weights, we can quantize them on a per channel basis, and that's widely supported in hardware. I've never actually seen a case where that wasn't supported in hardware. If you want an understanding for why this is a hardware efficient thing to do, again, I would point to the NVIDIA white paper, which I'll reference both in the description and at the end of this video, because it has an entire section dedicated to the per channel quantization of weights and why that is possible in hardware. And so it's nice. We can quantize weights on a per channel basis, and that means that each channel gets its own quantization parameters, so you can actually get quite good quantization resolution for your channels, because some channels have a larger dynamic range than others, but per channel quantization of tensors is very nice. Unfortunately, this is where the good news ends, because it turns out that for activations, you can't normally do per channel quantization, and this is because it's not supported in hardware. Again, the NVIDIA white paper gives a very good explanation as to why this is the case. That is actually very painful, that we can't do per channel quantization of activations. When you quantize a neural network, you can do something in Fake-quantize space where you can try just dequantizing the weights or dequantizing the activations, and you can see which is causing you the most problems. Is it quantizing weights that's causing the problems, or is it quantizing the activations that's causing you problems? So typically, when people do this analysis, they will find that they quantize weights pretty well and they don't quantize activations very well. And the reason people quantize weights well is for two reasons. One, because weights are static. They're not data dependent, they don't change. And the second is that because we can do this per channel quantization of weights, so we get quite good quantization resolution. People typically find that they don't quantize activations very well, and it's for the same two reasons. One, because activations are data dependent, so no matter what data you feed through the network, you need to use the same quantization parameters if you're doing what is called static quantization, which typically you need to do for runtime reasons. There's also something called dynamic quantization, but that typically isn't feasible if you're trying to get all of the benefits of int8. So this is a problem because when you feed data through the network, no matter what you feed to your network, it can be any arbitrary input, your activation tensors are going to use the same quantization parameters, and your tensors will be clamped and rounded down to that same quantized grid. That can be quite difficult. And worse, you can't do the per channel quantization of activations. You have to do it on a per tensor level, again, because of hardware reasons. So that is why quantizing activations can be quite painful. And that is it. It wasn't too quick, but hopefully it was useful. Here I'm going to link a few different resources. One is the NVIDIA white paper on neural network quantization. It's very good. It gives deep mathematical insight. And then the second is the Qualcomm white paper on neural network quantization. If you're just getting into int8, I would recommend starting with the Qualcomm paper just because it gives a broader introduction into int8 about all of the different topics, how everything works. And then for a more fine-grained understanding of what's happening in hardware, I would recommend reading the NVIDIA white paper. But that is it. That was the presentation. It was a broad overview of how quantization works. I will have many different videos diving into each one of these things in more detail, but that was the general overview. I hope that was useful. If you have any questions or anything wasn't clear or you'd like anything else to be covered, please just leave a comment. If it was a good video, please like and subscribe. And yeah, see you next time. Bye.